Welcome, everybody. It's my pleasure today to introduce Amber Wu, who will be telling us about topological data analysis in an economic context, property tax maps.
Great. Thank you, Henry. And thank you for the warm and kind welcome. And I'm glad to be here. So the title, as said, and this is a joint work with David from College of the Holy Cross. And also, will be an extended version of a talk we gave 2 years ago at IEEE conference. So let's begin. Okay, so the main motivation is we want to combine my interest with economics and math. I was econ and math double major when I was an undergrad. So property tax is one measure we're interested in, but why we're interested? Property tax is a very significant index in general in economics. It has direct correlation with housing value, which is a quite significant index in people's life and general evaluation of health of the economy. And also it has implicit correlation with various other economic measures. So towards the end of this talk, we'll show you how we try to compare our results about property tax patterns with other economic measures. So then why we use topological data analysis as the method. So in 2020, Fong and Porter published this paper that shows spatial applications of topological data analysis. You're able to use TDA to evaluate maps and then categorize them according to patterns, and then we'll have very interesting evaluations and findings out of it. So why not we also try some similar methods on basically property tags and see what we can find. So talking about spatial applications, we're definitely going to find some data with property tags, which is not just quantitative, but also have some spatial features. So that's why we turn to property tax maps. Those are information with both spatial features, but also it is closely related to property tax. Okay, so then we care about property tax not only by their numerical values. More, what we care is their heterogeneity patterns. So some previous study shows that actually the stronger the heterogeneity pattern is, it's more beneficial for economy. And also lack of variety in market framework is harmful. So it's really saying the same thing, but basically it's saying the heterogeneity pattern is something good and is desirable. So detecting such kind of feature would be helpful in general. Okay, so these are the motivations. And now let me guide you through about how this talk will be frameworked. So first, we're going to talk about what we actually do to our property tax maps. And then we are able to cluster it. So then we're just going to overview on what clusters we actually got. And then we'll furtherly discuss our results as well as we're going to compare to some economic measures, because now we are talking about property tax maps. Those are not just economic measures. So what about we just use some quantitative measures again and see if they're somehow related. So this will be the general framework. So now these are the raw data we have. These are from Property Shark website, and these property tax map layers are from publicly available resources. And so our sampling method is inspired by the Fong and Porter paper that we want to spread each sample parcel to spread out the city. And each parcel is 0.5 times 0.5 mile large. And the size is uniform in all the cities. And we choose 21 most populated cities that have available tax map layers in property tax, PropertyShark.com. Yeah, so as you can see, there are two different color schemes. So our research definitely take care of that. But the good thing is even though the color they use are not the same, the numerical values are consistent. So that's very convenient for our study. Okay, so we particularly want to study the relationship of a property tax of a given property comparing to its surroundings. So what we don't really want is this effect of street layouts. So we will consider two properties across the street as adjacent. So as a result, we do this processing on our sample, which we really do erosion method on the street so that we recolor the street pixel to according to its surrounding property values, so that we are getting a map or a process map that only have properties with their corresponding tax values. And you see that we assign each numerical, each color a grayscale color such that we are able to reprocess property tax maps of different color scheme into the same type of grayscale image. So that's some pre-processing of the image. And so now, in order to do filtration, these images are stored as arrays and each pixel has a numerical value. So how exactly do we assign those values? We basically just pick the median of each range of property tax values, except for the top and the bottom or the lowest range. Whenever the property tax value is below 1, we assign that property a 0.5 for each pixel. And whenever the property tax is above 10, we're going to assign each pixel a 10.5 value. So then you also see that there's one more legend that is, excuse me, there's one more legend that says there's no data. We don't want these type of property to particularly affect our analysis, so we're going to assign them different values. We're going to talk about this in a second. Okay, so now let's look at a zero-dimensional filtration of what I've showed you. This is the same sample that is being showing on the screen. So this filtration should be read from left to right, where in each image, the white area represent the properties with filtration value less than or equal to the current filtration value, where the black area is just the properties with higher property tax values. So we're doing a sub-level set filtration property tax values. And then in this case, no data property will be assigned value 12 because we don't want them to enter our subcomplexes too early to create connected component. We don't want them to be the generator of homology. So that's dimension 1. And okay, so one more thing before we come to dimension, sorry, that was dimension 0. One more thing before we come to dimension 1 is this dimension filtration tell us the pattern of the properties with the same tax value that are surrounded by higher tax values. So what about the reverse relationship? We're also interested in the properties that are surrounded by other properties with lower tax values. So that's why we're also going to do one-dimensional analysis. So you can see this filtration, but we basically do our one-dimensional filtration, use the negative of the function. So this filtration, the second line of the filtration should be read from right to left, where in each image, the white area on this side is going to represent the property that has tax value higher than or equal to the filtration value. So you see that's directly using the negative of the function. So here, again, we don't want our no data property to enter our filtration too early. So we're going to assign that a value of 1 such that it also only is going to be added to our filtration the last. So this will be actually a super level set filtration, but that gives us the one-dimensional homology of our map parcel. Okay, so there's a particular feature that I want to ask you to pay attention to that let's look at these, excuse me, let's look at this little white dot in the zero-dimensional homology. I hope we can see that. It wasn't there at 2.5, but it basically born at 3.5. So this is one connected component that born at 3.5, but it will persist even until 9.5. So we're not going to really pay attention to it persistent at this point. I just want you to pay attention to there's at least one component explicitly born at 3.5, and let's see we can actually capture that characteristic later in the persistence diagram. So we know that we are looking at the same map parcel. And then in the H1 dimension 1 analysis, I'm going to draw your attention to these two kinetic components. They basically born at the filtration value of negative 8.5, so 3.5 and negative 8.5. Okay, so now let's look at the persistence diagrams. So we see, I know this, I think this legend is a little hard to see, so let me just zoom in a little bit. Here, this is at 3.5, and then we have negative 8.5. So these persistent points represent the particular connected component I ask you to pay attention to. And if we look in the original map parcel that is shown on the left, you can see the corresponding property that is generating these persistent points, because this property has a property tax value of 3.5. It's between 3 and 4, and then it's surrounded by property with tax value above $10. So this percent point is not going to die until we reach 10.5 in our filtration value. Similarly, for those red property, that's the same idea. So we see that the percent point actually captures these particularly different properties in the original parcel that are surrounded by other properties with large difference in their corresponding property tags. Okay, and I see a question in chat. Let me look. So you're wondering how you get those same shape but switch colors. Yes, so great question. So one is interested in why we get exactly the negative of for the dimension 1 analysis filtration comparing to the dimension 0 filtration is because the way we compute one-dimensional persistence is exactly using the super level set of the filtration. So we can consider our normal zero-dimensional filtration like a sub-level set where we raise our filtration level, and all the property included is the property with tax value lower than the filtration value. But then if we want to capture the one-dimensional cycles in this graph, we are really capturing the complement of we were trying to capture. So basically we want to include all the properties that has greater tax value than the filtration value. So if we do this process backwards, we begin with the highest level tax value, we include the property tag we include the properties with tax value greater than the filtration value, and then we go down, that will directly capture the one-dimensional cycle of our graph, and but the filtration actually looks like a negative of the original zero-dimensional filtration. Is that clear enough? So one important thing here is the zero-dimension persistence should be read from left to right, but the one-dimensional filtration should be read from right to left. We basically intentionally reverse the order so that we see this interesting negative relationship. Great, no problem. All right, so we see that these actually are able to give us some direct, so persistent points are able to capture some direct heterogeneity pattern in the original property tax maps. So, but one thing here is because we assign each property discrete values, it's very common for persistent points to lie in the same location. So if you're curious about what are those circles in our persistent diagrams, the size of these circles directly suggests what are the number of persistent points repeated at the same location. So for comparison, it's not very handy to use a persistent diagram directly because we have to count how many points have the same set of values. So that's why we turn to persistent image. But why we really care about this repetition, because the more points, persistent points lie in the same location in our persistent diagram actually means there are repetition of same type of heterogeneity patterns. So there are multiple properties with the same tax value that are surrounded with other properties with the same gap in property tax. So we really want to capture how frequent is that repetition. So we go to persistent image. This is really, we place a Gaussian function centered at each persistent point and with a weighting function. So anyhow, this allow us to convert each persistent diagram into a image that will be a matrix of pixel values. So we choose 100 by 100 pixels, which after flatten will give us a 10,000 long vectors. So that will be very handy when we're trying to compare and cluster our result. So just for your reference, these are the actual functions. I hope they are readable in this size. So the first is the Gaussian that is centered at each persistent points, where this U1 and U2 are the birth and persistence of each persistent point. And then our persistent surface is really how we get the pixel value of each pixel, color value of each pixel, and that is really just a linear combination of our weighting function and this Gaussian. So our weighting function is defined as a ramp function. So this really means the pixel has higher persistence will be given more emphasis. So this is primarily because we want to reduce the noise in the data, because points with low persistence will be considered more likely to be a noise, but this is actually towards our advantage because persistent points with higher persistence actually also mean a stronger heterogeneity pattern in the property text maps. So we didn't adjust anything with the weighting function. And then the pixel value is really being calculated by doing a integration on each pixel range. Well, let's say over each area of the pixel. I don't think okay, I hope this function itself is self-explanatory. Okay, let me know if there's any question with these. Okay, so now if each map parcel is able to present it by a 10,000 long vector, we're able to cluster them essentially. So we use k-means clustering, but we know that k-means method has a certain level of instability. It really depends, it partially depends on where you choose the initial mean for each cluster. So we want to move past that randomness. So what we use is really an iteration-based frequency method on top of k-means clustering. What we do is we repeat k-means clustering for 1,000 times, and we record the frequency of any two given samples that are clustered together and normalize it as a frequency in our frequency matrix. So the result is after repeating 1,000 times, each while would give us the same frequency matrix. So the clustering result is now very stable after this frequency method. And we choose k equals 5 to be our k-num. So basically we start with 5 means clustering. We also tried 4 and k equals 4 and 6, but 5 is chosen to be the desired value. We compare the results. And so what you can see on the right is the single linkage clustering result. So this helps us to see the connectivity from our frequency matrix. So we do see that there's some general branches, which is indicating some large kinetic components, but there are also some nested structure inside each kinetic component. So we definitely take this into account when we're trying to determine our cluster. Okay, so here, since frequency matrix record all the pairwise frequency, we want to fix a certain frequency such that when we connect each pair with higher frequency than the selected frequency, we want a desired level of connectivity. So as you can see, 0.75 is the value we choose for the dimensional zero analysis, because for frequency value larger than that, we're going to have too many connected components where each component doesn't include many samples. So basically that means patterns in each connected component is not going to be very representative. But then if we use frequency values lower than that, we're just having too few connected components. And whereas we're having just a large connected components include everything, but then a little outlier connecting component. So that's also not what we want. So 0.5 will be our choice. And if you can see vaguely on this graph, there's 3 connected components. So as I just said before, we see some nested structure in each connected component. So we also try to capture that kind of feature. So that's why we use community detection algorithm on each of the connected components. We want to see if we're able to generate some subcluster, if we're going to determine some subcluster out of each connected components. So as you can see, we are able to do that. We actually detect 4 communities in the first connected component and 2 communities in the second connected component. And if you look at the graph, the third connected component actually behaves a little like a click. So that's why our community detection algorithm doesn't actually detect any subclusters in that connected component. And also the size of that component is not very large, so any subcluster will also not very be desirable. So that means we have 4 plus 2 plus 1, which is 7 clusters for a zero-dimensional analysis. Okay, so now let's look at, we really do the same thing for one-dimensional analysis. So the frequency, for the frequency matrix, we do the same number of frequency. We do k-means clustering for 1,000 times, and the frequency matrix again is now robust. And then we choose the frequency value to be 0.7, where we have again 3 connecting components. But now the third connected component is able to be distinguished into 2 subclusters. So for H1, for the one-dimensional analysis, we actually have 8 clusters. Okay. So now let's talk about what our cluster result actually, is it good or is it not satisfactory? So we use dimensional reduction method. The first thing we use is principal component analysis. We see that for the first 3 components, we have 73% variance preserved. So we believe that's most of the information. And if you look on the right, here is the all sample points. So they're colored into 3 different colors, indicating their different kinetic components, where blue is the largest kinetic component. So if you see in AII, those are the communities detected in the first kinetic components. And similarly in AIII, those are the community detected in the second kinetic components. And we see that in all these images, our clusters have clear boundaries. The points are nicely clustered according to each cluster. So we do consider our cluster result as quite satisfactory, at least in this visual presentation given by PCA. So now we also turn to another dimension reduction method, UMAP. The full name is Uniform Manifold Approximation and Projection. So what this algorithm really does is we pick a neighborhood size. So that is this beta number you see on the title of our graphs. This is saying for beta, the algorithm will combine this beta nearest neighborhood of each point, and they're going to interpret each neighborhood with locally homogeneous geometry. So they're trying to interpret our data set as a smooth manifold. So then we believe these visual representations basically tell us some local geometric relationship between our sample points. So as we tune this beta value, we're going to look at larger and larger neighborhood for each point. So we see that when beta is small, this is really focusing on very local geometric features. And we do see that our largest, this is actually going to be our largest cluster, this community 0 of the first kinetic component, it actually is detached. So we see that if we're focusing on very local features, the largest cluster is detached. That kind of says this cluster is having some different, intentionally different geometric features included in this cluster. So we're going to try to explain this in our cluster evaluation in a second. But then as we go further, if we make the neighborhood size larger, we see that at last, if we include almost all points in our neighborhood, our cluster is nicely grouped together. So we also see that our cluster is doing a good job when capturing some geometric features. So we do the similar thing for dimension 1 analysis. I'm just going to show you quickly. We see that the coloring is also very satisfactory. Okay, so let's talk about cluster evaluation. So what we do is recall that each person image is a 10,000 long vector. So we're able to compute actually cluster mean for each cluster. Those cluster mean will just be some artificial points. They don't have any property tax maps related to them, but we believe that those represent the main feature of each cluster. So we use the 3 samples that are closest to each cluster mean to be the samples with the representative feature. So then we examine those representative samples and then try to summarize their features, and we record the features in this chart. So to simplify the analysis, we just label the captured characteristics as weak, strong, low, and medium. And let me explain what those columns really mean. The generators really mean the predominant persistent points. So the points has high repetition. So the numbers recorded here are the range of the location of the range of the birth of these persistent points. And then the first part of the characteristic is capturing the heterogeneity. This includes either points with long persistent that they're off diagonal, and also points that take, also if we see the pattern that predominant persistent points are located in a vast range of domains. So that really means we have predominant persistent points located differently. So that's also some heterogeneity pattern we detect. And then the second entry of this column is recording the occurrence. So that's really the repetition of each persistent points. Okay, so to illustrate what we really are able to capture, I want to highlight these 3 clusters that we see the birth of their predominant persistent point are actually very similar, right? Something about 0.5, but their heterogeneity characteristic captured is somewhat different. So we see that they're really different in occurrence. Okay, so we're going to look into these representative samples and see how they reflect these labeled characteristic. Okay, so these are the 3 samples closest to the cluster mean of each cluster we labeled. So I hope we already can see that why we order them from low, medium to high. It's really the occurrence is growing if we go down and read those persistent diagrams, but also if we look into the original property map parcels, I hope we also can observe some increasing in heterogeneity. So we do believe that our analysis is able to not only capture, but also quantify these heterogeneity patterns that are recognizable even in the original party tax map parcels. But also we believe that we capture something more than that. We capture some more nuanced structure. So what is it is, recall that these are the 3 samples closest to each cluster mean. So basically they lie near the centroid of each cluster. So what if we move away from each centroid and go towards other cluster? Like what happens with those heterogeneity patterns? So now that motivate us to look at the boundary samples instead of representative samples. So before I actually show you the boundary samples, let's just look into this graph and see what's going to happen. So recall that this is the first PCA graph I showed you. This is all the points colored according to their cluster components, where each community is clustered otherwise. But now, since we're talking about clusters, I'm going to recolor all the points according to their clusters. So this is the same PCA projection, but we just recolor them according to their clusters. So now if you look at this zoom in version, the black points here are the artificial centroid cluster means that they don't have any property tax maps corresponding to them. But then the representative, so what we really want to talk about here, for example, is cluster 0 and cluster 3 that are the light green and this I don't know, blue purple color. So we're really talking about these two clusters. So the representative cluster I showed you should be close to these black dot. So we want to examine what happens on the edge of these two clusters. So now what I'm going to show you is the sample in cluster 0 that is closest to cluster 3 and the sample in cluster 3 that is closest to cluster 0. So we hope to see something nuanced from those samples. Okay, so here are the boundary samples. So we see that when moving away from the centroid, the heterogeneity pattern actually changed towards the features represented by the other cluster. That is saying, when I move away from the centroid of cluster 0, my boundary sample is having a higher occurrence. And when I move away from centroid of cluster 3 towards cluster 0, my heterogeneity actually, the predominant persistent points have relatively lower occurrence. The way we argue that is because we don't have those multiple persistent points around that predominant persistent points. So that heterogeneity actually is being weaker. But even if this happens, if we compare these two boundary samples, we do see that the boundary sample of cluster 0 still has a weaker heterogeneity in terms of occurrence compared to the boundary sample of the cluster 3. So we see that our cluster actually is the heterogeneity pattern captured is continuous, but even that we're going to have a clear boundary around our clusters. But this, what's worth noticing is this mainly happens around cluster 0 because our cluster 0 is the largest cluster. And what is included in cluster 0 is actually all the clusters with heterogeneity pattern, which is not strong enough to be clustered elsewhere. So it really groups up the leftovers. So that's why we really detect this kind of behavior between clusters. Okay. So we really do the same thing for cluster 1, one-dimensional analysis. And to sum it up, we really detect the similar structure where cluster 0 is really detecting everything that is left over, and other clusters are capturing things that are interesting, basically. You may see that there's one outlier in the representative sample of cluster 0. We can talk about that after talk. That's just one thing, and if you believe me for now, this doesn't contradict the framework we've found out. Okay, so that close up the cluster evaluation. So to furtherly summarizing what we actually are able to find, firstly, the zero-dimensional analysis and one-dimensional analysis are captured different heterogeneity pattern in property tax maps. So as an example, you can see that here we show two samples that are clustered together in dimension 0. So that means they're similar in the zero-dimensional analysis, but they're not clustered together in the one-dimensional analysis. So the main difference is this Hartford 10 is able to give us another location for the predominant persistent points. And that is really because aside of, okay, so let's zoom in a little bit. Aside of negative 4.5, so that is within this. So aside of those light blue properties, our Hartford 10 also have a wide spreading pattern for the light pink properties. So those are the generators in the one-dimensional analysis. So these are some heterogeneity patterns that are not very recognizable by human eyes, but we're able to detect them by different clusters, but also we're able to relate them back to the original map parcels. Okay, and then we basically just check if any of the city is having homogeneous clustering result. And since we randomly choose sample from each city, we don't actually expect any city to present homogeneous results. So this is as what we expected. And but you can see that San Francisco for the zero-dimensional homology is an outlier. That's just what it is. All samples in San Francisco exhibit very high heterogeneity pattern in our zero-dimensional analysis. But we do see that San Francisco is at least able to be separated in 2 different clusters in one-dimensional analysis. Okay, so then we also compare our cluster result to some very basic measures as mean and standard deviation. And just as expected, they are not correlated. Mean and standard deviation are just over summarizing patterns. So they don't have any direct correlation with our clustering result. But then what about, let's use some richer measure. So this is an economic measure. This is called Herfindahl-Hirschman index. I apologize if I'm pronouncing that wrong. I'm just going to refer to it as HHI. This is how we compute it. Basically, we're able to compute HHI for different things as long as we have mutually exclusive groups. So what this HHI actually captures is diversity. So a low HHI really says there's a high diversity, and high HHI indicates low diversity. So that's really what this index is about. And previous study with this index really shows that HHI, they use linguistic groups, is positively affecting housing price in the neighborhood. And also we see in previous study that housing prices are positively correlated with property tax. So we want to see if HHI of linguistic groups is going to say something about our cluster result. So we basically collect some information about linguistic groups and compute HHI for each sample we choose. So linguistic group data is collected by census tract. And what we really do is we basically just record the census tract included in each sample, and then we average the HHI among all the census tract. Okay, so here's the result. So recall the fact that lower HHI means higher heterogeneity. So one particular thing we can say is, if you don't remember, let me remind you that cluster 5 and cluster 6 in zero-dimensional homology are the clusters with relatively high heterogeneity comparing to other clusters in zero-dimensional homology. So if lower HHI is representing higher diversity, we would expect those clusters to have relatively low HHI. So we do see that several samples clustered in cluster 5 is having low HHI, but that is not quite true for samples in cluster 6. So we do believe that HHI is, so definitely something is happening with diversity in our clustering result, but our clustering result is definitely also capturing something different from that could be told from HHI. And this is also not very surprising since we couldn't really tell an HHI from a property tax map. So a weak correlation is already showing us, yes, we're in the right direction. Okay, so then one more thing we tried here is land use map. This is another available map layer offered from Property Shark. That is the website we use to collect our property tax map. So since I want to wrap my talk up, I'm just going to talk through what we found out. We didn't really repeat our analysis with land use maps. What we do instead is we just trying to observe if there's anything interesting comparing to land use maps. So here I showed you three samples. The main thing here is these 2 samples are similar in cluster zeros. These 2 samples are similar in the zero-dimensional analysis, and San Francisco 08 is similar to Cleveland 04 in the dimensional analysis, whereas San Francisco samples is not the same as Cleveland and Hartford in the zero-dimensional analysis. So we have some similarity and difference in H0 and H1, and let's just look at their land use map and see if we can find anything. So we do see that the San Francisco map parcel is having more properties that are of commercial use. So there's like a long list of legend, but really the takeaway is the yellowish colors is indicating residential use, and the oranges or the reddish brownish colors are indicating commercial use. So since we know that San Francisco is quite different from Cleveland and Hartford in zero-dimensional analysis, this is kind of indicating that in zero-dimensional analysis, if our property tax map, if our sample is having more properties with commercial use, it's likely that it's having more heterogeneity that is captured in zero-dimensional analysis. But since we know that these two samples are actually close in dimension 1, but we don't really see any similarity in land use, we kind of want to argue that land use doesn't really tell us anything that is able to be detected in dimension 1. So we do enlarge our observation into more samples. Basically, we choose 4 cities in California, and actually the cluster result for those 4 cities are basically all the samples in those 4 cities lies in 3 clusters. So we basically group the land use maps corresponding to each sample into the corresponding cluster, and we want to observe if there's anything that worth noticing between our cluster result and land use maps. So what we really could tell is that more homogeneous property land use, especially in residential, that means implies potentially more homogeneous property tax patterns, but this is only in zero-dimensional analysis. Land use maps are not a good indicator for the one-dimensional heterogeneity patterns, and also more diverse residential land use in zero-dimensional analysis is potentially indicating it's a stronger heterogeneity pattern in property tax. Okay, so a summary of what we've done is we really showed topological data analysis is applicable to property tax maps, and so that we are able to classify parcels based on geometric features, and we identify different patterns of heterogeneity that are recognizable in the original map parcels, and it cannot be obtained by analyzing related economic parameters. Okay, will be my talk, and thank you. These are the references I've talked about in this PowerPoint.
Thanks so much. So before we get to questions, let's briefly unmute ourselves and clap for Amber. All right, so questions for the speaker. So Eric, go ahead and unmute yourself to ask your question, otherwise I'll read it out loud.
Oh. Hey, really cool work.
Yeah.
My question is, did you consider making random tax maps just to have a baseline of how this whole TDA pipeline works if there's no underlying pattern in the first place?
Yeah, we haven't thought about it, but that would be a cool thing to try. What we actually tried is making some, it's not random. We tried to make some artificial person image. Those are the average of person images in each cluster. So those are like kind of fake person images, and we basically did some comparison on that, but we soon find out the main problem is for those artificial person image, those doesn't have any real life implication. There's no property tax map we can affiliate that to. So then regenerating property tax map from the beginning sounds like a good idea. That would be something we could try. Thank you.
Amber?
Mm-hmm.
Thank you for a nice talk.
Thank you.
I have a question about how do you characterize the relation of the TDA method you use and the cluster method?
Sorry, can you repeat your question? How did I categorize?
how do you characterize the relation of the TDA method you talked about before and the cluster you use later? Are you use it to verify whether the cluster is good or not? Or
So okay, I'm not sure if I'm answering your question, so please let me know if that's not the direction you're asking for. But the logic here we aim to follow is we're really trying to see if topological data analysis is applicable to property tax maps. So what we do is really we just do persistent homology on property tax maps, and then we do clustering, which is a natural choice of clustering method. And then we want to see if the cluster we get is informative, if it gives us something that worth studying. If it is, that means yes, applying TDA to property tax map has some non-trivial values. So and I hope our finding do prove that.
so you applied cluster first to see if it is worthwhile to further study by TDA?
Yes, it's kind of like that logic. So we really just do the analysis and then we evaluate the result and see if all of those work is worthwhile, if that tell us something meaningful. And we do believe we find some patterns that are meaningful.
Oh, thank you. Thank you for that.
No problem.
That really clarifies a lot.
Thank you. And I do see a question in the chat.
So it asks any analysis of maps across time, so time varying maps.
Right, definitely. We haven't tried it. And also the thing here is we haven't found any good resources just regarding property tax maps because we were just focusing on that, and the frequency of Property Shark updating their value. Updating their data is kind of tricky, so we don't have a good source of that. If we do have a source, this sounds a really good thing to try, especially if it's like something with property, because it's not like landscape map images that has like more complicated changes over time. Properties normally, if you don't have any specific construction, they are kind of fixed. So it sounds like a time series study would be very interesting. Oh,
Eric asks in the chat if you've received feedback from people with economics or city planning backgrounds.
thank you. We haven't. I probably should just go forward and reach out and see if they have any thoughts about our work. Thank you for that direction.
I had a question. So for sublevel set filtration, you have 0 and 1-dimensional homology. And then for super level set filtration, you have 0 and 1-dimensional homology.
Yes.
I think you maybe talked mostly about 2 of those 4. Have you experimented with the other 2?
So yes, so actually the main use of super level filtration is just to compute the H1 for sublevel set filtration. That's just our
That's
goal.
right. Like H1 of the sublevel set is really closely related to H0.
Yes.
Of the super level. Oh, I see. So you're saying that there's 4, but
I
in
think there are
pairs, they're
only
very
2 of them. Yes. We're just doing 0. We're just detecting connect component because it's easier in computation. So we just use the negative of the functions. Yes.
Right. So you're always using the computationally more efficient one.
Yeah. Sorry, I cannot hear you, I think, somehow.
Somehow you're not muted on Zoom, but we can't hear you.
But I think the microphone is not detected or somehow. Sure. Yeah, you can type it. Oh, not
Right.
perfect
So Teresa puts in the chat.
Thank you.
Yeah. Closely related, but not quite the same. Along with that.
So right. Okay. So now let's make this rigorous. So yes, I think if it's I should just look into the method, but yeah, so if that's the case, it's worth investigating that on our data then.
You
But
could
so
imagine
far,
there's boundary effects, for example.
yes. Thank you.
Okay. Any last questions or comments? Well, thanks again, Amber, and let me end the recording here.
Thank you.